Okay, in today's lecture, we're going to cover the section 5.2 material on double integrals over general regions. So in our last section, we introduced the idea of a double integral of a function of two variables integrated over some rectangular region R. Now in this section, we're going to consider evaluating double integrals, but no longer over rectangular regions. So in this section, we're going to be considering integrating a function of two variables over more general bounded plane regions. So recall that a region in the plane is bounded if it can be enclosed in a circle. That is, if it doesn't extend infinitely in some direction. Now, for any bounded plane region, we can classify that region as being one of two types. So we would say that a region, let's call it D, in the xy plane is a type 1 region if it lies between the graphs of two continuous functions of x. So that is a set of points xy where x ranges between two constant values, a and b, and y is bounded above and below by functions of x. Let's call them g1 and g2. So geometrically, let's look at what a type 1 region would look like. So here in the xy plane, let's suppose that we have two functions. So their graphs are some nice smooth curves. Let's say where the upper curve is the function g2 of x, and our lower curve is the graph of g1 of x. And we're looking at the part of the xy plane that lies between the graphs of those two functions on some x interval from a to b. So if our bounded region can be described as being bounded above and below by functions of x, then we would say that region is a type 1 region. Now, to evaluate a double integral over a type 1 region, we're going to make use of an iterated integral. So here we would define the double integral of a function f of xy over the region D in terms of the following iterated integral. So our inner integral will be with respect to y, where y was bounded above and below by functions of x. Let's call them g1 and g2. So the upper and lower limits of integration for the variable y are these functions of x. So when we evaluate this inner integral with respect to y, we get back a function of x, and we will then integrate that function with respect to x over our x interval, say from x equals a to x equals b. Now, in a similar way, we can define a type 2 region. So we would say that a region D in the xy plane is a type 2 region if it lies between the graphs of two continuous functions of y. So that would be a set of points in the xy plane where the values of y are bounded above and below by constants c and d, and the values of x are bounded on the left and right hand side by functions h1 and h2 of y. So as an example of a type 2 region, we might have some region in the xy plane that looks like the following. Let's say we have two curves which are not considered the graphs of functions of x, say if they don't pass the vertical line test, but we could think about these as the graphs of functions of y. Say x equals h2 of y would define this right curve, and x equals h1 of y would define our left curve. And we're looking at the region that is bounded on the left and right by those curves, and then above and below along the y-axis by constant values c and d. Now, to evaluate a double integral of a function over a type 2 region, again, we would make use of an iterated integral. So this double integral of that function over d would be evaluated by first integrating our function with respect to x, where the values of x are bounded above and below by functions of y, h1 and h2. And then we would integrate with respect to y over the y interval from c to d. That's defining our region. So we can now integrate these functions of two variables over any general bounded plane region. We just need to know whether our region could best be described as a type 1 or type 2 region. Or we'll see some examples of regions that could be described either way. So let's look at an example of this. In this first example, we are asked to evaluate the double integral of x cosine y over the region D, which we're told is the region bounded by the curves y equals 0, y equal x squared, and x equals 2. So usually for these double integral problems, we want to start by sketching our region to see whether we could best describe it as type 1 or type 2. And in this example, we are looking at the region bounded by the curves y equals 0, so that is the x-axis, the curve y equals x squared, which is a parabola opening upward, and the vertical line x equals 2. So we would have the following shaded region, which we'll call capital D, for our region of integration. So again, this upper curve was the graph of x squared. Our lower curve was bounded by the x-axis, and then this vertical line on our right edge was the line x equals 2, and then our curve x squared intersects the x-axis at the origin when x is 0. So this region could be described as type 1 or type 2, but I would think it's a little easier to describe as a type 1 region. So let's write out how we could define this region D. We'll say as a type 1 region, the set D, or this region D, could be described as the set of all points x, y, such that x lies between 0 and 2. We see along the x-axis, our range of values is from 0 to 2, and the value of y is bounded below by the x-axis, that is y equals 0, and it's bounded above by the graph of our function x squared. So as a type 1 region bounded by functions of x, we could describe D in this way. So to evaluate the double integral of x times cosine of y over this region D, we would use an iterated integral where our outer integral is with respect to x from 0 to 2, and the inner integral is with respect to y, where the bounds on the variable y were 0 and the function x squared. So here our integrand is x cosine y. We're integrating in the order dy dx. So from here, it's just like the iterated integral problems that we saw in the last section. We would first find our antiderivative with respect to y, which would give us x times sine of y, and we evaluate from y equals 0 to x squared, and then integrate with respect to x. So here we have the integral from 0 to 2 of x times sine of x squared, And then we subtract what we get when we plug in 0 for y. Now sine of 0 is 0, so we're not subtracting anything here. And then to evaluate this integral with respect to x, we would need to make use of a substitution. So here I'm going to let u be x squared, in which case du is 2x dx. And we could then rewrite our integral as 1/2 the integral of sine of u du. And our limits of integration, let's change from x values to u values. So for the lower limit, when x was equal to 0, we find u is 0. And for our upper limit, when x is 2, u is equal to 4. So we have, for our antiderivative, a negative 1/2 cosine of u evaluated from 0 to 4. So when we plug in 4 for u, we have negative 1/2 cosine of 4. And then we subtract what we get when we plug in 0. Now cosine of 0 is 1, so we're subtracting a negative 1/2, or adding 1/2. And if we want, we could simplify a little bit by factoring out a 1/2. That would leave us with 1 minus cosine of 4. So this would be the value of the double integral of that function over this region D. So let's look at another one. In this next example, we're asked to find the volume of the solid that lies under the elliptic paraboloid, 3x squared plus y squared, and above the region D in the xy plane, bounded by y equals x and x equals y squared minus y. So we know that to find the volume of a solid under some surface and above a plane region, we're going to evaluate the double integral of that function over the region. We just need to know whether this region would be type 1 or type 2. And in this example, the region that's being described is bounded by two curves, y equals x and the curve x equals y squared minus y. So if we want to sketch this region, let's start by finding the points of intersection of these two curves. So since that second curve is given as a function of y, to find my intersection points, I'm going to let the x values equal each other. So for my first curve, x was equal to y, and for my second curve, x was equal to y squared minus y. So we find, if we move everything to one side, we have 2y minus y squared is 0. So I can factor out a y. I'm left with 2 minus y is 0. So y could be 0 or 2. So our points of intersection for these two curves are 0, 0 and 2, 2. So let's sketch our curves. Here in the xy plane, we have the line y equals x, so that is the line of slope 1 passing through the origin, and we're looking at the points of intersection for our curves at 0, 0 and 2, 2. And then our other curve, x equals y squared minus y, is a parabola opening along the positive x-axis, since we have a positive y squared coefficient. And its y-intercepts are 0 and 1. So we have a parabola that looks something like this, and it's intersecting our line at 0, 0 and 2, 2. So we're talking about this shaded region. So in this example, we could think about this region as being a type 2 region a little more easily, since it looks like it's bounded on the left by a parabola and on the right by this line. It's a little easier than thinking about this being bounded above and below by functions. So let's describe this region D as a type 2 region. So here as a type 2 region, D could be described as the set of all points in the xy plane such that my y values are ranging from 0 to 2, and the values of x are bounded on the right and left by these curves. So on the left-hand side, we have the parabola y squared minus y. So x has to be greater than that parabola and less than or equal to the line x equals y. So let's evaluate our volume as a double integral. Here it would be the double integral over the region D of the function 3x squared plus y squared. And setting this up as an iterated integral, we would have our outer integral with respect to y from 0 to 2, and the inner integral from y squared minus y to y. And our function was 3x squared plus y squared in the order dx dy. So let's start by finding our antiderivative with respect to x. We would have x cubed plus xy squared, and then we're evaluating from x equals y squared minus y to x equals y, and then integrating with respect to y. So we have the integral from 0 to 2 of, when we plug in y, we have y cubed plus y cubed, and then we subtract what we get when we plug in y squared minus y. So we're going to have y squared minus y quantity cubed, and then we're subtracting y squared minus y times y squared, and integrating with respect to y. So let's see what we have here. This is the integral from 0 to 2 of 2y cubed minus, if we expand y squared minus y cubed, we have y to the 6th minus 3y to the 5th plus 3y to the 4th minus y cubed. And then we subtract, if we distribute our y squared in that last term, we'll have y to the 4th minus y cubed dy. So combining like terms, we're left with the integral from 0 to 2 of, we have a y to the 4th, we have a 4y cubed minus 4y to the 4th plus 3y to the 5th minus y to the 6th dy. So finding our antiderivative with respect to y, we have y to the 4th minus 4/5 y to the 5th plus 3/6 or 1/2 y to the 6th minus 1/7 y to the 7th, which we are then evaluating from 0 to 2. So let's see what we get. Substituting 2 in for y, we have 16 minus 1/28 plus 32 minus 1/28/7 minus, when we plug in 0, we are left with 0. And then this simplifies to 144/35. If we get a common denominator, we can simplify our answer to this form. So again, pretty similar to that first example. Here, some of the details in our second integral were a little tedious, expanding this y squared minus y cubed term, or getting our answer in simplified form is a little bit messy, but not too complicated overall. So let's look at some other ones. In this next example, we are again asked to find the volume of a solid that lies under a paraboloid x squared plus y squared and above the region D in the xy plane, bounded by the curves y equals x squared and y equals 2x. And in part A of this example, we're asked to evaluate the integral where we're considering D as a type 1 region. So as we did in that last example, let's start by finding the points of intersection of our curves that bound our region, in this case x squared and 2x. So if we let these functions equal each other, we have x squared equals 2x. So moving everything to the left-hand side, we have x squared minus 2x is 0. And if I factor out an x, I'm left with x minus 2 is 0. So x could equal to 0 or 2. So here the points of intersection of my curves would be 0, 0, and 2, 4. So let's sketch our region. Here in the first quadrant, we have the curve y equals x squared, so this upward opening parabola, y equals x squared, and the line y equals 2x, which is the line of slope 2 passing through the origin. So here our points of intersection were 0, 0, and 2, 4. Our upper curve is the graph of y equals 2x, and our lower curve is the parabola y equals x squared. So we could think about this as a type 1 region. It's bounded above and below by functions of x. So let's call this region D. And as a type 1 region, D could be described as the set of all points xy, such that x can vary from 0 to 2, and y is bounded below by the parabola x squared, and above by the line y equals 2x. So to find our volume for this solid, we would be evaluating the double integral over the region D of our function that defined the surface, in this case x squared plus y squared. And to evaluate this double integral, we could make use of an iterated integral, where our outer integral is with respect to x from 0 to 2, and the inner with respect to y from x squared to 2x. So here our function was x squared plus y squared, integrated in the order dy dx. First finding an antiderivative of our inner function with respect to y, we would have x squared times y plus 1/3 y cubed, and we would evaluate from y equals x squared to 2x, and then integrate with respect to x. So let's see what we have. Here we have the integral from 0 to 2 of, plugging in 2x for y, we have 2x cubed plus 8/3 x cubed. And then we subtract what we get when we plug in x squared, which would be x to the 4th minus a 1/3 x to the 6th dx. So combining our x cubed terms, we have the integral from 0 to 2 of 14/3 x cubed minus x to the 4th minus 1/3 x to the 6th dx. So let's find our antiderivative. For our first term, let's see, we would have 14 over 12 or 7 over 6 x to the 4th minus 1/5 x to the 5th minus 1 over 21 x to the 7th, and we're evaluating from 0 to 2. So here, when we plug in 2, let's see what we get. We've got a 7/6 times 2 to the 4th is 16 minus 32/5 minus 2 to the 7th is 128 over 21. And then we subtract what we get when we plug in 0, which is 0. So simplifying, if we combine these terms, we're left with, I believe, a 1,944 all over 315. Okay. So in part A, we found the volume of our solid, thinking about it as a type 1 region D. And in part B of this example, we're asked to evaluate that same volume, but where we're considering D as a type 2 region. So here, let's look at this region D again. It was in the first quadrant of the XY plane. We had the region bounded by the curves y equals 2x and the parabola y equals x squared. Now, if we want to consider this as a type 2 region, we would have to think about it as being bounded on the left and right hand sides by functions of y. So here our left curve was the line y equals 2x, or solving for x, we would have y over 2. And then our right-hand curve was the parabola y equals x squared, or solving for x, we would have root y, where the values of y can range from 0 to 4. So as a type 2 region, this region D can be described as the set of points xy such that y ranges from 0 to 4, and x is bounded on the left by y over 2, and on the right by the square root of y. So to find the volume of our solid, we would be evaluating the double integral of the function x squared plus y squared over the region D. So as a type 2 region, we could set up the iterated integral where our outer integral is with respect to y from 0 to 4, and the inner integral with respect to x from y over 2 to the square root of y. And here our function was x squared plus y squared in the order dx dy. So we have the integral from 0 to 4 of, if we find the antiderivative of the function with respect to x first, we would have a 1/3 x cubed plus x times y squared, evaluated from y over 2 to the square root of y, and then integrate with respect to y. So we have the integral from 0 to 4 of, plugging in the square root of y, or y to the 1/2, we have 1/3 y to the 3/2, plus y squared times the square root of y would be y to the 5/2, minus, when we plug in y over 2, we have a 1 over 24 y cubed minus a 1/2 y cubed dy. So combining our y cubed terms, we have here the integral from 0 to 4 of 1/3 y to the 3 halves plus y to the 5 halves minus, let's see, 1/24 and 1/2. 1/2 would be 12/24. So we have altogether minus 13 over 24 y cubed. So let's find our antiderivative. Here we would have a 1/3. The antiderivative of y to the 3 halves would be a 2/5 y to the 5 halves. Plus antiderivative of y to the 5 halves is 2/7 y to the 7 halves, and then minus we have 13 over 24 times 4 is going to be 96 y to the 4th, evaluated from 0 to 4. So in the last part of our work, let's simplify. When we plug in, we have a 2/15 times 4 to the 5 halves. Well, if we take 4 to the 1/2, or square root, that is 2, and then 2 to the 5th would be 32, plus 2/7. 4 to the 7 halves would be the same as 2 to the 7th, or 128, minus 13/96 times 4 to the 4th, I believe is 256, and then we subtract what we get when we plug in 0 for y, which is 0 in this case. So after some simplification, well, we should get the same volume that we got by evaluating this as a type 1 region. So here, this had worked out to 1,944 divided by 315. So we see that in part B, when we were considering this region as a type 2 region, it resulted in an integral that was a little bit messier to evaluate than that first one. So for some of these problems, if our region can be described as either type 1 or type 2, usually we want to go with the approach that yields a simpler integral. Or depending on the function that we're integrating, we might have to use a certain order of integration in order to find our antiderivative. So we will see some examples of that in the second part of this